Hey everyone, continuing our discussion here, aircraft instrument systems. We're up to the magnetic compass. Take a look at that one. All right, geographic north. Um, Basically, the theme is that geographic and magnetic north are not going to be exactly the same. Uh, Geographic north is, in effect, uh, if you could extend the North Pole and the South Pole into like axes, that's where the Earth actually revolves around the axis. If you were to run an axle all the way through the Earth, but that doesn't necessarily mean that's where the magnetic poles line up. For navigation purposes, though, there is a system that's based on true north, uh, and there's a system that with including the North Pole and the South Pole. In order to fly from one location on a chart to another, the pilot must have some sort of instrument that will maintain a constant relationship with this grid. The device pilots have relied on for this purpose is the magnetic compass. A limitation of the compass is that it measures direction relative to magnetic, not geographic north. So, in effect, all of your charts, you're going to have to make an adjustment. However, it is an effective navigation tool, except when you're near the North Pole. And as you can even see from the diagram, magnetic North Pole seems to be some degrees south, at about 7:30 on the clock dial. So yeah, if you're at the North Pole, magnetic is going to actually theoretically show south of you rather than north. Okay. Um, the pilot has to correct for variation, the variation between true north and magnetic north. The inner workings of the magnetic compass. It's a simple, it goes back some time also, and it's reliable. The main body is a cast aluminum housing with a glass lens. A vertical reference mark called a lubber line is painted across the lens, and they're showing that in the diagram. Let's say the lens is going to get placed over the assembly here. Inside the housing there is a small brass float which rides on a low friction post. That would be the little axis that the top type mechanism is actually balancing on. A compass card with a dial graduated in 360 degrees is connected to this float. And you can see that's the black part. It's added right on top of the float there. Two small bar type magnets are soldered to the bottom of the float, aligned with north and south. You can see those are the magnets they're talking about. There's compensating magnets on the south. This diagram is also showing a sensing magnet. We're mostly concerned with the compensating magnets because there's a little place that you can adjust that. You can see the compensating screw, which is a way that you can actually get in and adjust your compass. Filling the compass bowl or the housing, it's filled with compass fluid to dampen the oscillations of the float. The fluid is a hydrocarbon product similar to kerosene, but with additives to keep it clear. The housing must be completely full with no bubbles. All right, so don't leave a bubble in the top. Try to fill it completely filled. This one looks like it's got a bubble, doesn't it? Question. Magnetic compass bowls are filled with a liquid. Why do you fill it with a liquid? Why can't we just leave it with air? Is that to retard precession of the float, or to reduce deviation errors, or to dampen the oscillation of the float? All right, we just saw that in the prior slide. It is to dampen the oscillation of the float. That's why it's filled with a liquid. I imagine if it's just air, it would have oscillations. What is the fixed line mark attached to the compass bowl of a magnetic compass called? Is that the reader line, the lubber line, or the reference line? That was that line. We pretty much skated over it. It does have a name. Since they asked the question a few times, after you've already reviewed the question once or twice, the word lubber will be what you normally would go to. Lubber line, that's the marking on a magnetic compass. And, some other instruments that we may get to. Gyro, instruments. All right, so we talked about true north. Now, magnetic north, this is explaining it as if the Earth itself was a magnet, and that there's the poles of the Earth. There's our actual magnetic North Pole and a magnetic South Pole. They just happen to be close together. I would imagine some planets would rotate almost on their totally on the side, 90 degrees away from the magnetic North Pole. I'm not sure what is common, but that's more for astronomy. The pilot's compass correction. The magnetic north and south poles are not located at the geographic poles, yes. The angular difference between the true and magnetic poles at a given point is referred to as variation. So that's a variation from one to the other. Not the other problems that they talk about with compasses, and that's deviation. So this one is variation. The difference between the North Magnetic Pole and the geographic North Pole. You can also look into what is the North Geomagnetic Pole. It's something that I've looked it up before, but it just doesn't come up enough to stick so far. So if somebody's got an interesting story about it, maybe it'll stick. We have come up with different charts to kind of show what the degrees of variation would be. And the zero, where you need no adjustment, just happens to be, it goes through the panhandle of Florida. So you can imagine if the 5-degree west is out to sea, South Florida, it looks to be about 2 degrees west. Out of 360 degrees, that's pretty darn close. Of course, there's extremes. You're 90 degrees away in North New England, in the Maritime provinces, and even more extreme when you're off to the west side of the country. And you notice the lines don't quite follow the north-south that you're used to on a map. What is that called? So basically, variation in the western United States is 17 degrees. So, okay, we can see where 0 is, where's 17? There's 5, this line's 10, this line's 15, so 17 is about where this aircraft is located. Since the magnetic North Pole is located to the east of true North Pole in relation to this point, the variation is easterly. And you can see they're showing the 17 degrees here is from the aircraft, from true north to magnetic north. And the variation is to the west. So true, you want to go to the true as opposed to the magnet, so it's west of the magnetic north. Isogonic lines connect points where the variation is equal, while agonic lines define the points where the variation is 0. So I guess the agonic line is the line that between the darker and the lighter portion of the country. And the rest of the lines are called, what's that called? Isogonic. Oh, there it is right there in Texas. I wonder if my audio's doing any better. I did look at another YouTube video under settings to apply a filter. I'll try that after this one, but I don't think you can do it right now as I'm recording. I probably can, but that's probably not the best way to do it. Alright, so we talked about variation. The other one is deviation. And the illustration shows motorboats with the engines. And you can see the engine has an effect on the compass, in effect. The north wants to point towards the engine. So you can basically figure out on an aircraft how much does it deviate, and you can adjust for the deviation. It's disturbances from magnetic fields produced by metals and electrical accessories within the airframe itself, or the aircraft. A magnetic field surrounds almost every wire carrying electricity. You might not notice it, but a compass will. Almost all the steel parts of an aircraft and the engine have some magnetism to them. And there's magnetos, alternators, generators. Those are strong magnetic fields. And if they're close to the compass, it will influence it. So basically, to minimize the electrical connection, this is where you'll use the twisted to line. Probably more of an avionics question. But yeah, that's to reduce electrical interference. In case you're wondering why they twist the to line. You'll see that with telephone wire. In order to compensate for variation, you adjust the compensating screws based on a procedure called swinging the compass. Now that does require that would be a good project, but basically like there's two compensators, two or more small compensator magnets located in the housing that may be adjusted to cancel the effect of most of the local magnetic fields in the aircraft. So it's deviation, not variation. I'm sorry. So you swing the compass to account for the magnetic fields that are aboard the aircraft. Normally you do that. Let's see if I have, is there a slide on that? No, maybe not. When swinging the compass, the technician adjusts the compensator magnets to minimize deviation. And apparently you do it two ways, with the radio on and the radio off. Any remaining error is recorded on the compass correction card. It's in effect a record of your adjustments. When swinging a magnetic compass, the compensators are adjusted to correct for A, deviation, C, oscillations, or B, or C, magnetic variations. So compensators, that was not the variation between true and magnetic north. It was the deviation caused by the magnetic fields on the aircraft. Okay, I'm in the red a little bit. Back it off. So what do we decide? This is deviation A. You just have to get the two words in order: deviation and variation. An aircraft magnetic compass is swung to update the compass correction card when would you actually swing the compass? Probably if you're adding some equipment that's going to affect the fields. But let's see what the options are. An annual inspection is accomplished. At B, the compass is serviced. Or C, equipment is added that could affect compass deviation. So there's the answer I was looking for. Yeah, I mean, it doesn't change. It's the same equipment. So if new equipment comes on, you'll probably have to re-swing the compass. To correct for the deviation error caused by you adding more equipment. Otherwise, there's no time interval. In what way do magnetic fields generated by electrical equipment and steel parts in the airplane affect the magnetic compass? Well, they're probably looking so that you can somehow slip the word deviation into your answer. Stray magnetic fields caused by wires and equipment, and particularly magnetos, alternators, and generators, will actually cause a deviation in the accuracy of the compass, and you can compensate for it with compensating magnets. Swinging the compass, the guy would have shut me up a long time ago. Let me see if I got the right words in there, though. Yeah, stray magnetic fields deflect the compass from correct alignment with the Earth's magnetic field. Yeah, normally a sentence is fine. If they want a second sentence, they'll be quiet and let you continue your thought. What is the reason for swinging a compass, and how is it accomplished? Basically, it's the same type of answer. It's to compensate for equipment that might have been added that creates a different magnetic field. And how do you accomplish it? You actually go out with a little correction chart, and there's an area at the airport. It's called a compass rose, and you can actually line up the aircraft with true north and adjust your compass so that it agrees with the compass rose on the tarmac off the side of one of the taxiways. Oh, just by adjusting the compensating magnets. Which of the following causes of aircraft magnetic compass inaccuracies may be compensated for by mechanics? Is there a chip paint on this one? We can always fix the chip paint. Let's see, deviation, magnetic compass current, whatever that is, or variation. So there's your two words, deviation or variation. Obviously, we've been talking about deviation and adjusting compensator magnets. So the technician may adjust for deviation. That's why they have an adjuster on it. If we couldn't, they wouldn't have a means for us to do it. You're in effect turning the magnets inside the compass, which is kind of interesting. It's fascinating how they come up with this. We're looking at one of the FARs, the Federal Aviation Regulations. It's all under 17 CFR. So the parts are the main numbers. Okay, 23. We're getting into more of the specific regulations for aircraft in the 2300 series. In this case, yeah, it's not even early on in 23. It's a section of that. It's subpart or subpart 1327. So, and then they get down to the magnetic compass. So what does it say that we need? Its accuracy, a magnetic direction indicator. Its accuracy is not affected by the aircraft's vibration or magnetic field. So it's kind of what we've been talking about. 2, the compensated installation may not have a deviation in level flight greater than 10 degrees on any heading. Which we can get it a lot more accurate than that, can't we? But once the aircraft travels, especially if it's traveling west, the degrees of a deviation would increase. So I suppose you'd have to factor that in. What's the second part? A magnetic non-stabilized direction indicator may deviate more than 10 degrees. All right, so it may not deviate over 10 degrees, and it looks like they're going to give us some exception. Okay, so while you're running your electric windshields or your windshield heater or something to that degree, some temporary usage, I guess. And you have to put a placard, a little warning next to it, if it's going to be over 10. So what's that? Under that's part 23. I'm not sure what the question's going to be. It's got to be something close like that. The maximum deviation during level flight permitted in a compensated magnetic direction indicator installed in an aircraft certificated under FAR Part 23 is, drum roll, 10 degrees. Nice. And I know I'm kind of in the way here. Let me see here. Can I move myself? That probably isn't helpful. Alright, maybe can I make myself smaller? I think that's Alt. Oops, that doesn't exactly work. Oh well, forget it. Tell you what, I'm just going to go to the desktop. What are 2 items that should be considered during inspection of a magnetic compass? I think there's a list of like 6 that they'll have you pick from. You only have to pick 2. I would imagine security of its mounting bracket. Basically whether or not the fluid is clear, not cloudy or bubbly, and that the lubber line is clear and it can easily be read. I suppose we can add in deviation, since we can inspect that now. Paint chips. Let's see what they say. Fluid must be clear. Housing must be full with no bubbles. The card must be legible with the rubber line intact. So the card is actually the part that's on the float that actually turns around. And the compass should be properly calibrated. I'd say we didn't use the word calibrated, but normally you'll get a little label. Oh, I guess it's the end. Okay. All right. Well, not too bad. Okay, we'll end it there, and I'll see you in the next time. All right. Have a good one.